ID 011-014-80, subject consequence of design and detail, lecturer Paul Johnson, recorded 24/4/80.
Sydney architect Harry Seidler was appointed visiting professor in architecture at the University of New South Wales for the first semester of 1980. He was born in Vienna in 1923. After studies in England, he graduated from the University of Manitoba in Canada. Later, he did postgraduate work at Harvard University under the founder of the Bauhaus, Walter Gropius, and studied design under the painter, Josef Albers. In 1948, Seidler started to practice in Sydney, and the many buildings he has completed since then have earned him an international reputation. Amongst his best-known buildings are Sydney's Blues Point Tower, Australia Square and the MLC Centre, and Canberra's Trade Group offices. A recent overseas work is the Australian Embassy in Paris. In this lecture, Seidler deals with his experience in evolving a technical vocabulary from design concepts. He speaks of the consequence of design and detail.
Architectural design essentially considers three things which must be brought into unison. The very act of designing a building involves a three-way simultaneous process, which brings into a happy marriage considerations of planning, structure, construction, and aesthetics. Now, we have dealt with matters of aesthetics by looking at the correlation that is evident between the forces that mold much of 20th century art and that which has influenced much architecture. Today, I think it may be of importance to deal with the other considerations in this simultaneous design process, which is how design results in the tangible final result, and that is the structure and the method of construction of the building. There are two things that must be basically considered, and that is how much labor is to be exerted in achieving the task, and what kind of and what method of material assembly should be used. Now, in the past, architecture has been very labor intensive, and that really is the difference between traditional architecture and the aims of the architecture of the 20th century. Initially, tentative moves have been made to innovate and use new materials more efficiently to achieve the results in building. And this has been brought to our time in the latter part of the 20th century to the point where the balance between material and labor has to be a particularly delicate one because of the expense and unavailability of on-site labor and the development of quite sophisticated industrial devices to prefabricate, to pre-make, and then assemble by mechanical means on the site elements of buildings. Now, the level of appropriateness of just when it will be reasonable to make something in the factory, bring it to the site, erect it by crane, and when it will be more reasonable to simply use essentially traditional labor-intensive operations. That balance and that degree of appropriateness is the very consequence that every design brings with it, because no shape can be conceived unless it's the consequence of what it means in terms of physical implementation is at the same time and simultaneously considered. Now, it would be a very different thing to build in countries such as India or Mexico, such as I have done in the past, or in places like the United States or Australia. In the first two, there is ample labor, very cheaply available to do and perform almost any task on the site. Labor that is not very spoilt. They will be willing to do quite dirty tasks, difficult tasks. Whereas in the United States and Australia, if one demands such tasks to be performed, they will be extremely uneconomic, very, very expensive. Whereas the techniques and technology that's available in those more developed countries bring into focus the opportunity to use industry to do much of the task. Now, whatever the balance one finds will inevitably depend on the size of the task. Because if we build a one-off small structure or one-off highly specialized and molded structure, it will be labor intensive. But that may well be the only way of achieving the result. Those who rather naively suggest we should now build houses by entirely industrial methods will find that it's unreasonable, because unless you produce 100,000 virtually identical elements every year, it would be uneconomic to set up mass production lines to produce such a commodity. Whereas if there is a huge repetitive building of substantial proportions needed, it may be entirely reasonable to set up production line because of the alternative being economically quite unattractive. There's one thing clear, I think, that in the 21st century, we will not readily find people who are willing to perform dirty tasks, labor-intensive, heavy muscle work on top of scaffolds, in other words, to pour concrete in midair, wearing gumboots, and all the things that go with it. We will simply not have people willing or economically willing to perform such tasks. And therefore, the tendency is to get away from the handmade product and to bring it more and more within the realm of industry and technology. But whatever the balance we do find, and the techniques that are appropriate at this time and in this place are in flux. They will vary. They will change with economic conditions, industrial development, and labor relations. Now, what we'd like to look at now is going through a period of history, say, during the last 30 years, and just see what kind of balances can be brought about by this interchange between on-site labor in the traditional sense and using the products of technology in a certain varying degree of balance and cooperation in order to achieve very different type of results. Now, here is a simple structure depending purely on its support on a skeleton of minimal steel. Only 4 columns support a platform which is relieved from its structural task by means of these hangers that relieve the load of these long horizontal members. On both sides of a support, a cantilever is relieved as well as a mid-span is relieved. Now, this is minimizing the amount of material, but this material is obviously made in the factory, erected on the site, and then filled in with a hand-wrought, lightweight structure that completes the building. And this was done some 30 years ago. I think this kind of technique in its purest form, such as this almost is, has not had much influence on building as a whole, because people tend to dilute the clarity of a concept far too much and simply expediently use whatever comes to hand. And it doesn't really depend so much on new materials as much as a frame of mind in how one attacks a problem. The problem in this case was the use of traditional materials, economic because they are lightweight, readily achievable, timber frames, but timber frames brought to a distant site in the mountains for a ski lodge, erected on the site by minimal technology, and then filled in by hand labor to achieve the total result. Now, the frame is the key to it because the building got started very quickly by having these 5 vertical frames which help hold up the structure. Without them, the building would have been entirely handmade, whereas by pre-assembling, pre-computing the main structural elements and also make them help in the whole organizational pattern of the building, because the floor levels are supported at different levels on this frame. So instead of corridors, there in fact is only a staircase in the center of the building, fusing all areas of it to each other. And the frame becomes the dominant element of the whole concept, which is to be expressed, to be exposed, and be naturally visible, both on the outside as well as on the varying levels on the inside. So here some benefit and some balance has been found between those diverse problems of pre-assembly, technologically made elements, and hand labor. When the problem is to minimize the task even further, as in this case of a temporary building, it is inappropriate to use technology in the conventional way to ask of it to create a structure, to assemble a structure that will be quite elaborate, resist bending moments, but in favor of that, the choice has been made here for a hyperboloid structure, which is a minimal surface, the most torsion-resistant surface, as being the appropriate one, because it lends itself to the production by the assembly of straight line skin elements. Now here's the hyperboloid. We can see the totality of it. Part of it is only used above the ground. The rest, of course, doesn't exist. But this being the ground level, a exhibition hall has been built, which really is a half of a hyperboloid. Now this hyperboloid will have the advantage of being able to be assembled, as I say, by, in this case, pipes, and by devising a system that will allow us to assemble these pipes readily, we can then erect it in a minimum of time, take it down in as short a time, have the building reusable, and cover it on the outside with a material that performs the task that is required, which is to stay there for a month or so, be waterproof, and also allow light to be transmitted to the inside. So you get a translucent kind of tent structure. But what is evident is the form is related to the technique of achieving it. And the technique is the use of pipes, which are squashed at the ends, connected by a special patented element here, which we will see later in a bit more detail. And that can be pushed together and brought about very quickly. In long span buildings where the need is to have no columns inside a vast area of covering some acres, this use of pipes, in this case made into space frame structures, is an appropriate answer of industrial technology applied to this problem. Now here we have a warehouse building which it consists of the same kind of pipes erected to result in enormous spans. And this is the way the pipes actually are produced by industry. The pipes are squashed at the end, they are serrated at their tips, and these long surfaces produced by an industrial process, their length are computed automatically by a computer, and these are then assembled either on the ground and lifted up, or on minimal scaffolding in the ground, on the ground. And these chucks, these central cylinders, form the housing for these pipes to be slid into. A very rigid, a very ingenious method of using standard industrial components of varying thickness. Depending on the load in each particular member, the thickness and the diameter of these pipes, of course, varies. But here we have technology, the design, directly related to the concept of the building. It's an outcome of it. Now, when it comes to the one-off, unique, special building, it would be inappropriate to use sophisticated industrial techniques, but rather the use of modern structural technology is, of course, in order. But the aim here is to build a concrete building which would be as least labor intensive as can possibly be devised. And this is done by having the floor levels flat, no beams under it. This is easy to pour on scaffolding, and to create those elements that carry the weight as upstanding rails or walls to result in a stiff channel-like form which can perform the structural task asked of it. And the result of this is then evident in the way concrete is used to be formed and poured into wooden molds that are easy, straightforward to produce, and that is its essential aim. Even a garage structure, such as the one over here, by just using 150 millimeter thick concrete walls, but the way they are shaped into a box-like form gives the whole structure innate stiffness, which enables it to hang out this large distance from its support, a great cantilever, which any one of these component elements would not be able to do, but in unison it can perform the task. Now, when it comes to, here's the suspension of this enormous overhang of a garage, made possible by the use of slab, both horizontal and vertical concrete slab, joined together to form rigid boxes. When it comes to the vertical support, I think the question is, now, is it reasonable to build such vertical supports of concrete also? And the answer would be no, because if you were to form a concrete support of these proportions, of some 1.5 meters or so, you could carry a 20-story building with it. It would be inappropriate to use concrete for that purpose. But instead, something more easily involving less hand labor was assembled by the combination of steel reinforcing and hollow concrete blocks. Now here, concrete blocks of the conventional variety with holes in them, with steel rods passing through them, and more steel rods pass through them at the point where the major supporting task is to be done. And in that way, we get a vertical element, quite thin, holding up a poured-in-place concrete floor, which is the more useful material for that particular purpose. A lot of buildings are in the nature of repetitive floors or special floors to serve needs of occupation, and the building is not really high enough to warrant building it of a frame, that is to have an internal rigid skeleton on which the external walls are hung or the floors are supported. And for that reason, such buildings are very often simply the layer cake of floors supported by traditionally laid and produced walls. These walls may be rough split concrete block in themselves, also produced by technology, or they can be conventional brickwork. But the same thing applies in that the whole supporting surface of the wall carries then layers of the floor which are poured in place concrete, clearly visible on the outside. And the same can also apply to multi-story buildings, because even if there is a frame that holds the building, there still is the need to clad the building externally. And such cladding may be produced entirely by industrial methods, such as hanging panels of concrete on the outside of the building, but where they vary too much. You have too many different types, and therefore it becomes uneconomic, and the conventional material is resorted to, such as brick. But the brick here again is carried by ledges of the floors brought to the outside, be it a staircase. These are landings of a fire stair repetitively, and this behind here are lift shafts. So the code and regulations say every second or third floor has to be tied, and brickwork is supported in between. But the directness is important, to build a frame and directly give full support to the infill material. The repetition of even a poured-in-place concrete structure is important and will have a direct consequence from its design. And that design says there shall be columns to serve the purpose of particular width of units. These are maybe 4 meters apart or so. And the formwork that produces the beams, that produces the columns, that produces floor, slab edges, or beams, as the case may be, are of a unified, repeated use form. So you make one, or you make 5, pour concrete into them, disassemble them, and reuse them progressively, vertically in the building. Often the task, of course, is to produce the almost impossible in terms of minimal labor application and the right kind of balance being found to use technology to best advantage to produce the absolute minimum cost multi-story structure. Public housing has often asked these questions. What can be done to build hundreds of flats needed urgently? And the answer in this case is by means of partly industrialized, partly on-site devices that builds 2 parallel buildings, but because we don't want to interrupt the system that is developed for these buildings, the interruptions, the inevitable interruptions, such as lift wells, and to some extent stairs, are placed in between them and not made part of the repetitive labor-saving process that's developed. And the minimal size structure that can be conceived really in concrete is a single span slab, a slab that has continuous support on 2 sides and spans a short distance, something like 4 or 5 meters across between walls. Now, how does one produce the walls? And the walls, if poured vertically, would be very labor intensive to produce. So the device here used is to pour them on the ground, and by mechanical jacks to slowly lift them up into a vertical position so that they may act as the continuous support for the absolutely minimal cost horizontal slab between them. And this is the device used on these Housing Commission flats in Rosebery. One can see the vertical walls stood up, the horizontal slabs poured in place, and then the cladding is provided by industry, flat slabs of concrete bolted to this frame, made in the factory, and these external galleries, L-shaped units produced by industrial methods also. The interruption to the system would have been lift shafts, and they are, as was pointed out, actually placed outside the buildings. Here we have the run of the mass-produced building, as it were, a building produced by some sequence of operation, whereas this structure that provides the support for the elevator and the bridges leading to the building is in fact a hand-wrought, conventionally built, poured in place concrete structure. And here the hangers, to minimize the specially needed supports. A lift shaft is very rigid in itself, a box vertically, almost like the garage we saw used horizontally. And from it, it is quite capable of supporting hangers that can emanate from it and give support to these access bridges, which would otherwise need special vertical support. Now, when the scope of the object is much broader, and that is the scope of repetitive, a huge building housing some 3,500 office workers in open landscaped offices, the opportunities for production of such a building brings it much closer into the sphere of technology. Because if the task is to build repetitive office space of this nature, some 16 meters across without any columns and a long span between the supports, all the office part can be produced by technology, whereas the specialized access cores, both access for people, lifts, services such as toilets and air conditioning shafts, that is a specialized, ideally then handmade product. So you get the mix between that which can be readily mass-produced in the way of the long span structure, fully repetitive, so it is warranted to go to quite a level of sophistication to produce it, whereas in the cores are then essentially handmade, although clad in this case with external prefabricated panels. Now, the system of construction is such that it brings into unison only 3 industrially produced components, which is a column, a long span beam, and a floor plank. And they are connected by pre-stressing wires to produce the unity. Here's the 3 elements in a tryout situation, a prototype, which was tested in an attempt to assess the structural viability of each member. They performed very successfully. So mass production and sophisticated lifting, hoisting equipment was resorted to, which is an outcome, of course, of the choice of such devices, to assemble the building in a minimum of time. Once you have a production line going, making these 3 elements, you can assemble them fairly quickly. But it does, of course, take, and it is proven to be economic when the scope is large enough to even go to the expense of such moving gantries as these are in the erection of the units. Now, the units themselves are attuned to the structural task asked of them. Here, the 16-meter long floor planks are shaped to reflect what is the structural need, which is to have a T configuration in the center of the span, and for that T to merge into a rectangle more and more toward the support to resist shear. This would be a very difficult thing to produce by conventional means. And here it is actually exposed in the building. On the undercroft of the structure, you can actually see these elements freely. And the upswept shape of them, which is a structural, logically arrived at thing, allows services to run longitudinally in the gap that is left at their upswept ends, which is most useful for integration of mechanical services. Now, how does one produce such elements? Obviously in pre-made molds. In this case, there are 4 molds in order to keep up with the need of the rate at which these elements are needed. A steel mold here is empty, ready to receive the steel harness, the reinforcing, which is then put in, concrete poured, and here you see an element finished after steam curing overnight being lifted out. And by having several of these molds, one can make a specialized production procedure which produces these elements, which, as they are completed, are stockpiled, and then the crane comes, picks them up, and puts the whole thing together almost like a mechano set. But each individual unit is really not enough. What makes the structure viable is the way in which these units are connected. And they are connected by means of pre-stressing wires, both vertically and horizontally. The facade elements are tied into the floor elements, and one can see the actual stressing points at on the exterior of these long span beams. Here's a detail showing that each floor plank is pre-stressed and has its anchorage at the end. There's a floor plank, and where it is joined into the main facade beam, its stressing is continued through the web of the facade beam and anchored on the exterior and made fireproof with a steel cap over it. Now, this thinking of combining or developing components that can do structurally remarkable tasks given a large volume of production leads one to the investigation of just how appropriate the shape can be to serve a particular task. And here there is really no limit within economic viability, no limit to the span that one can produce almost with such elements. And here's one, even if the last one spans something like 24 meters, this one spans something like 35 meters. An enormous length, conventionally quite unachievable, but with pre-stressed concrete, quite possible, as long as the form of the element is attuned to its task. And the task is to resist bending as a simple beam, which means a maximum of concrete at the top in the middle for compressive resistance. And in other words, the flange of this beam widens at the top, whereas conversely, the bottom of the beam isn't needed at all from a compressive point of view. All the tension takes place there. The pre-stressing cables go past there. So it is thin. It is narrowed from the support. And at the support, the element is solid to resist shear and form the anchorage points for the pre-stressing tendons. And such elements would normally be considered unachievable if one had to build conventional formwork. But when you repeat it, as in a multi-story building such as this planned for Hong Kong, it is possible to make one mold, plan the production far enough ahead to result in a very beautifully shaped element, almost Baroque in form, but achievable only by quite sophisticated one mold only. But once that mold exists, I think there is no limit to how many one can go ahead and in fact make. In the case of a long span beam being of advantage to a design, the consequences to come to the realization it would be unfeasible to make a mold of the sophisticated type just seen. So when you only want one or two of such things, but they are still demanded or ideal for a design, then their shape has to be devised so as to be achievable by more handicraft methods of making the formwork. As in this case, it's a single, not a multiple curve, not a compound curve, but a single molded shape that changes this element from an eye section in the middle to a solid one over the support, it being a pin-jointed structure resisting substantial spans and moments. So the form is a direct consequence of the means of production that are considered economic in any particular instance. The integration of such structures with the mechanical installations are in their infancy, I think, in architectural thinking. Very often, or too often, we find it that however sophisticated the structure, however economically it is produced, the remainder of the services that are needed in the building, such as air conditioning ducts, are simply considered an afterthought and done, as it were, almost any old how, fitted in by highly labor-intensive means. Here is an example of a building that attempts to systematize and bring into the industrial processes the means of mechanical services. And they happen in between the strength of these pre-stressed units. In the center between units, this being the core of the structurally carrying concrete elements, such as we have seen. In between them run the mechanical services, taking advantage of the fact that longitudinal supply ducts can run under their upswept ends. The prerequisite for this is for a building to be fully sun protected, and that makes mechanical sense so as not to attract substantial heat loads as are so usual in so many recent buildings that are all covered with glass. But here the lighting, the air conditioning run in between the webs of the structure, and the structure itself is in fact molded into a light fitting, using the structure to reflect the light that is thrown up onto it to give diffused daylight throughout the artificial light throughout the interior, and it then, the mechanical services are as industrially produced as are the structural components. It doesn't mean, of course, that once one accepts the viability of such industrially produced components, that special things, a stair, a bridge, are then also in need of being made in the factory. They would be inappropriate. There's only one of those, so they are simply produced by poured in place conventional techniques. But here we have the intertwining of a supply duct and cross ducts with the lighting fitted above them in, for instance, a library, where this is very appropriate, clear open space to arrange book stacks and whatever the interior demands are, and the hand-in-glove relationship between structure and mechanical services. A very different consideration applies when we build high-rise buildings as against any lower structure, because the great demand in a high-rise building, such as the circular tower at Australia Square, is for it to be produced quickly, and its very concept of design is that of repetitious elements that can be made not so much entirely industrialized, but by techniques that involve a serial production, even if performed on the site. And this building has two floors particularly that are of which the demand is to carry heavy loads. These first two, the others are repetitive floors and have radial beams. All the columns are the same, but the technique of building the building itself brings the industry to it by making the exterior forms of the columns in the factory, filling the columns with concrete on the site, and in that way getting a structure that is not in need of any scaffolding. We can see the hollow forms made in the factory here filled with concrete, but just to show how these interlocking ribs, which are derived at by the development of isostatic structural force lines. Just how does one achieve such a thing in reality? And here a simple method of production was used to achieve the tangible result. The first, you make a mold, then you mold out of bricks, then you plaster that mold, then you make a master mold in it. You turn the master mold upside down, and then you mass produce the pans that are finally used as permanent formwork on that floor. So the steps then in physical terms are the production of a mold made initially out of rough brick. Then it is plastered on the outside. It is then used as the base of a master mold. That master mold is turned upside down, and on it is placed steel reinforcing, which in turn forms the basis of producing every one of these types, which are reused all the way around the circle of the building, and then placed on minimal formwork, concrete poured on top of them, so as to result in this visible form on the ceiling, on the soffit of the lower floor. When the task is to build a really exceptionally high building with as least time lag between the production of one floor and another, in other words, the greatest rapidity, which in commercial building, or in almost any building really, means economics that are quite substantial. In other words, how long does it take to build a floor? Here, a cycle of 4 days per completed floor was achieved in such a multi-story building, 68 floors of it, supported by 8 very substantial columns which attract a lot of the load for greater lateral stability. And these columns change from bottom to top of the building. They, in fact, are, one is wider at the base. The column is wider at the base and gets narrow at the top. And here's are these industrially produced components being lifted by crane and assembled to result in these heavy supports for the structure. The long span beams, similarly, the external mold of them, not the whole beam, but only the external form of it, made by industrial techniques, embedded on the outside with the appropriate finishing material, in this case white quartz, and these are then assembled by this technique of spreading the workforce vertically by having on the reinforcing of each major beam act as the support for subsidiary beams, and the space between these little subsidiary beams, really the reinforcing for ribs, is then spanned by small plastic pans which can be removed, and thereby the production changes rapidly from bottom to top, and the workforce is spread over something like 4 or 5 floors. And that speeds the whole method of production, which is unique to the problem of building high-rise buildings. Here the assembly of the column components, and the end result, of course, shows this, the components quite freely. The joints are simply allowed to be visible. The theater, which is attached to this large tower in a circular configuration, was produced with a by similar means to the heavily loaded floors at Australia Square, with this intertwining ribs, far more critically dimensioned in order to resist the bending, which requires great depth of a section, as against the narrower and wider but shallower width of these same ribs at the support. So the structure actually bends downward, as well as consisting of these interlocking ribs. Again, the pans were mass-produced, placed on formwork, concrete poured above them. Once steel is placed into these interlocking ribs, and the totality then takes on this form, rather beautifully reflecting the structural demands of a circular form heavily loaded above and deriving continuous support from a drum-shaped wall, and reflecting the needs of maximum bending, deep and narrow, as against sheer, wide, and shallow in terms of the cross-section. And these considerations, one a direct outcome of the other being the design as against the consequence, what it means to implement this in constructional and economic terms. Rather unique systems were devised by French contractors with us for the construction of the Australian Embassy at Paris. The complex consists of two buildings, an office structure using long span beams, which we have seen before, and an apartment building. They're both curved for good reasons in order to achieve good outward views in one particular direction, but let us just dwell on the means which were employed to implement and support this building. There are two such structures, orientated and curved, one convex, the other concave, in order to see the Eiffel Tower and beautiful views held from the building. Now the office structure consists of fully viable structural facade units. That is, these boxes on the outside in fact carry all the weight of the exterior of the building. There are no columns as such, but the precast elements carry the whole load. Where it is considered appropriate and desirable from the internal design of the building to interrupt the regularity of these supports, because the supports are undesirable, for instance, where there's the need for an ambassador's balcony. He is to be given somewhat more consideration than all the others in the building, and at the top of the building. Hand-wrought, special, poured-in-place reinforced concrete is substituted for the mass-produced industrial component that forms the rest. There's a clear differentiation in color and texture. And here, these structurally produced components are seen being lifted up. You can see one standing there, and the floor elements from it deriving their support on its inner edge. Here, the facade elements propped up temporarily on the facade and waiting to receive another layer of the floor structure. Now, the floor structure is systematized. Its design is a curved building, and one would think very difficult to mass produce, but not so, because each component, when made wedge-shaped, narrower here, wider there, you put them all together and you get a curved building. So no penalty paid for having a curved building. And the facade elements are so small that they're all straight anyway. So here's a way in which these were assembled. Here we have the structural facade, and these units that span across, configured the same way as we have seen used before, and lifted up by very sophisticated cranes that are available in France. Unfortunately, in our country, in Australia, it is very often a matter of being afraid to use such devices. We could use cranes of this nature, but our industrial relations are such that it is a hazardous procedure to bank on. In other words, the minute all the crane drivers go on strike, everything stops. And that is something that makes the use of these elements less frequent here than it is in other parts of the world. The advantage, of course, of these long span units is a complete freedom for internal subdivision, this being a typical floor in the embassy, which is then used for various office purposes. The facade is interrupted. We cannot see this terribly well but in this picture, but there is a large special support placed under the building. This is the height of the building, and there is a specialized support produced to create the main entrance of the building. Here we can see it better. It is a support that will pick up the building above and all the floors that rest on it, and take the load and bring it inward into a small point of support in the center, so as to allow cars to drive in and drive out again, forming a covered entrance. Now, how does one shape such an element? Obviously, it is not something to be produced by industrial means, but the demands of structural design are paramount in the forming of such an element. And the most rigid transitional forms and structures are inevitably hyperboloid, or surfaces that join and produce quite diverse areas, such as a curve from above with a rectangle down below by means of straight lines. And the straight line formwork is something that is quite visible on the outside of the end result, that is straight timber forms tapered to produce rather beautifully twisted surfaces into which concrete is poured. No, sorry, I meant to go forward. The techniques of making such elements requires obviously a substantial amount of handwork. But this handwork is minimized again if there is a little bit of repetition, as in the case of this apartment building, which has its own structural exterior above carrying floors. But here, at least, there are 6 elements used to pick up this entire building, because it was desirable for it to be more open at ground level to give support, to give access, than would have been the case had this structural facade been brought right down to the ground. So the formwork was produced to pour into it 6 of such elements straight, balancing the curved load that comes into it from above and ending up in a circular caisson support against the ground. And giving expression to laws of statics produces some quite beautiful forms, but the form is only as viable as the method that can be devised to achieve it, which is straight timber boards. And here is the mold that was actually used and used repeatedly to form these supports. Not unreasonable in economic terms to make one such thing out of straight boards that are tapered each in order to achieve that result. Here it is when seen from the side, how the quite sinuous curve of these elements reflect the structural task that they have to perform. But finally, the most ingenious technique used on that building by the French is an invention that is entirely French, and it's called prédale. Normally, for a curved building of this kind, which would involve quite labor-intensive operations to produce formwork on every floor, which would vary, be wedge-shaped elements and so on, to produce a curved building. But the French went about it by separating the flat slab floors into 2 layers, one that is precast on the ground and the remainder that is poured up in the building. On a steel platform on the ground, the shape required is made by simply having edge molds going around the piece that is needed. It is only about 7 centimeters thick, that is very, very thin, and one would think in large panels of this nature impossible to lift up. But by this ingenious device that uses pipes and pulley-carried cradle, such a very thin slab, this one is 50 square meters, a whole apartment, is picked up on, with cables and pulleys. Now the effect of the pulleys is to equalize the load in each one of these points that it is picked up all over its surface, which means that one can pick up a very thin slab without breaking it, able to lift it up and deposit it on minimal scaffold on the building and lower it down and of course do away with entirely all conventional labor-intensive formwork. And the top surface of this slab is left rough so that steel is placed on it when in position. The rest of the slab is poured and the building proceeds at quite an exceptionally fast rate. The underside of these slabs, of course, can simply be painted and are complete. Now, to sum up, I think what should be clear is that architectural design, any concept, is only as viable as the techniques that are envisaged and proven to be economically possible for its implementation. Without it, I think we only plan castles in the air.